Welcome Pure Maths 3 students to week 16 of maintenance. Right, first one here, we're solving an inequality. Now the important thing to notice here is that on one side we have modulus sign and on the other we don't. And this is going to make things a bit more complicated if we use the square method, which I will do, but you just have to be aware when you're using this squaring method and you've got something, a modulus on one side and not on the other. So when we end up expanding this, we should get x squared minus 4x plus 4 greater than 4x squared minus 6 minus 12x plus 9. I'm going to bring everything across to the right hand side, so I should get 3x squared minus 8x plus 5. And then I can factorize that, so I get my critical values from there. I think it should be minus 5 here and minus 1 here, and that will give us, yep, okay. So we're getting some critical values there of x equals 1 or 5/3. Now, at this point, hopefully you would have been aware, like I've already pointed out to you, that we've got a modulus on one side and not on the other. So this complicates things. Normally, if we'd had a modulus on both sides, we could have just gone and drawn this equation, and we'd have something here at 1, something here at 5/3, right? And it'd be like this, and we'd want this bit under here, wouldn't we? But because there's not a modulus on both sides, it's not going to work the same way. So we're going to have to do some testing. Let me just show you why. I'll do a little sketch here. If I was sketching the modulus, maybe something like this. This is 2, and we know that the modulus would look something like this, the modulus one. And then we've also got this 2x minus 3 business, so that would cross at minus 3. It's a line, but it's quite a steep line, so every time you go across 1, you go up 2. Okay, and you can see that it's only ever going to cross once, and there's only one place where the modulus blank here for the moment, to 2 times 1 minus 3. So this gives us 1 minus 2, which is negative 1, but modulus makes it into a positive 1. 2 times 1 minus 3 was minus 1. So that's true. Okay. So it's greater than the modulus of x minus 2 is greater than 2x minus 3 at 1, so that's fine. Now let's try 5/3. So we go 5/3 minus 2 modulus, and we're going to compare that to 2 times 5/3 minus 3. Now on the left hand side we get 5/3 take away 2. So take away 2 gives us a negative third, which when we put the modulus sign we get a positive 1/3. Now let's compare it to the other side. We get 10/3 subtract 3, and that gives us 1/3 as well. So they're equal at that point. Okay, they're equal. So that point at 5/3 is this point here where the two equations meet. So since that's where they meet, before that point you can see that the modulus of x minus 2 is greater than 2x minus 3. So we would report our answer then as x is less than 5/3. So the reason I wanted you to do this one is it's just a bit different, having a non-modulus sign on one side and a modulus on the other. So you have to think a bit more carefully about those. Okay, hopefully that's helpful. The next one, we're solving this equation here. We've got some logs. So we're going to use our log rules. I'm going to write ln x plus 4 on this side is equal to, and then I can rewrite this as ln x ln x 4x squared using my two log rules. So first of all, the log rule to move that as a square, and then because we're adding logs, we can just multiply the 4 and the x squared. Then we can get rid of the logs, so we've got x plus 4 is equal to 4x squared. I'm going to bring everything across to that side. And then we can solve this with a quadratic equation. So we could say x is equal to minus 1, or 1, plus or minus the square root of -1 all squared minus 4 times -4 all over 2 times 4. You're going to get two answers out of there. One of them is going to be a negative answer, and one's a positive. So x equals 1.13 or negative 0.883. We can actually ignore this answer because if you have a negative, if you try and apply that negative value here, it's undefined, right? Okay, ln's undefined for a negative x value. Okay, so there we go. The next one, okay, so we've got to use a double angle formula, I think is what they want us to do here. Now, the double angle formula for tan is this. So for cotan, it's just the reciprocal, isn't it? So I could write 1 minus tan squared x over 2 tan x plus, and then cotangent x is like 1 over tan x equals 3. And I could just multiply this whole fraction by 2 over 2. And you'll see then I'll have the same denominator. So I'll get 1 minus tan squared x plus 2 all over 2 tan x equals 3. And then so in my next line, I can go 1 minus tan squared x plus 2 equals 6 tan x. And then I'll bring everything across to the right hand side, so I get 0 is equal to tan squared x plus 6 tan x. And then I think it's plus 3, plus minus 3. And then we can perhaps use the quadratic equation there. So tan x, chuck that into your quadratic equation. Now when I do that, I'm getting two values. I'm getting minus 3 plus or minus 2 square root 3. Okay, you can do that. We've done quadratic formula before, so I'm not going to bore you with the details there. And therefore x is equal to, now I would use first this and then this to get my principal values. I'm getting 24.9 and negative 81.2 as my principal values. But you can see that the range that they want me to be looking in is between 0 and 180. So this one is fine, but I just need to get this one within my range, so I'm just going to add 180 to it. So if I add 180 to it, that will give me 98.8 degrees. And those would be my two values within the range that I've been asked to find. Okay. Okie dokie, so the next question here is a differentiation question. We're trying to differentiate this curve, find the gradient function, and we know that it's got one stationary point, and we've got to find the exact values of the coordinates. So what I'm going to do is use the quotient rule. I'm going to say u is equal to e to the 2x, which means that du dx is equal to 2e to the 2x. I'm going to say that v is equal to 4 plus e to the 3x, and therefore dv dx is equal to 3e to the 3x. Then I'm going to apply the quotient rule. So v, which is this here, 4 plus e to the 3x. I'm going to multiply that by du dx, which is 2e to the 2x. My mistake. Subtract u, which is e to the 2x, into dv dx, which is 3e to the 3x. Then we're going to pop that all over v squared, which is 4 plus e to the 3x, and I'm just going to square that whole thing like that. Now, I guess we can expand everything here. So on the top line, what are we going to get? So we get 8 e to the 2x plus 2 e to the 5x. Now, I'm getting that 5x because when you times e to the 3x by e to the 2x, you add the powers there using your index laws, minus 3e to the 5x, and that's all going to be over that 4 plus e to the e to the power of 3x, and that's all squared. And we can simplify that again, so that whole line at the top now becomes 8 e to the 2x minus e to the 5x, and on the bottom just stays the same there. Now, ready. We know there's a stationary point. We want to find the exact coordinates of the point. Well, the gradient function is equal to 0 at a stationary point. Now, to get this equal to 0, we're going to take that top bit, the numerator, and make that equal to 0. And because to get a 0 from the top line has to equal 0 to get a 0 gradient. Now, so we can rearrange that to this, and then I can get 8 is equal to e to the 3x, and then I can take ln of both sides, and that will give me 3x, and then so then x is equal to 1/3 ln 8, or if I want to be fancy, I can say, well, that's the same as x equals ln 2, because apply my power rules there, sorry, my log rules there. Excuse me. So that's the x value of my stationary point. Now, how do I find the y value? Well, I'm just going to insert this x value that I've just got into here. So let's do that. The y value is going to be e to the 2 ln 2 over 4 plus e to the 3 ln 2. Now we can simplify this a bit, can't we? We can say, well, that's like e to the ln 4 over 4 plus e to the ln 8, and e to the ln, that just cancels itself out, so you're left with on top 4, on the bottom 4 plus 8, which is 4 over 12, which is 1/3. So the coordinates are ln 2, 1/3 of the stationary point. Okay, so let's move on. The next one's a parametric equation. And we're going to find dy dx. First we're going to find dx dt. So I'm looking at this and I'm saying, I've got to, I could do it slowly by using the chain rule, but we're probably getting good enough now to just look at it and go, okay, it's going to be minus 4a, and drop the power down, cosine 3t, and then there's the sine t there as well. If you're having trouble with doing it in your head, you want to go back to the chain rule, okay? And then dy dt, and I can show you what I mean. So I'll just do this last one with the chain rule. Let's say that u is equal to sine t, and so du dt would be cosine t, and we know that y is equal to a u to the 4, and so dy du is equal to 4a u to the 3, and then we put them together, dy dt, in this case actually, sorry, would be this one multiplied by this one, so it becomes 4a, now u was sine, so it's sine t, sine cube t, and then cosine t. Okay, so that's what we get over here, 4a, and maybe I'll write it like cosine t sine r cube t. So just remember you can use that chain rule that we did on the side there. Okay, now therefore dy dx is equal to 4a cos t sine cubed t, and all over negative 4a cosine cube t sine t. You might be thinking why? Well, because we can write this as dy dx, is dy dt multiplied by dt dx, so I'm just timesing by the reciprocal of this one here. Okay, so hopefully that makes sense. Now we can do some cancellation. So good night, drop one of those off, make it a squared, get rid of that. Drop one of those off, make it a squared, get rid of that. So all up, I think we should be looking at negative sine squared t over cosine squared t, which is the same as just negative tan squared t. Now, the next part of the question says show that the equation of the tangent to the curve at the point with parameter t is this here. So you know that the equation of a tangent is going to follow a straight line straight line formula. So why don't we go ahead and find out what c is. Okay, so we know that y is, according to this part of the question here, this, and x is this, and we know what our gradient is, so we're just going to insert all of that nonsense in here. So we get a sine to 4t equals negative tan squared t times x, which we said was a cos 4t, and then plus c. Okay, so at this point, we get c is equal to a sine to the 4t plus, and I might write this as sine, this is the tan bit, sine squared t over cos squared t times a cos to the 4t. And we could perhaps simplify that you can see that we could cancel that out and then change that to a squared. So we should get a sine to the 4t plus sine squared t a cos squared t. Okay, now that's our value for C. Now we're showing if we've got parameter t, the equation is going to be this. Now you see we've got our x and y values here. So what I'm going to do is write my equation. I'm going to go I'm going to go y equals mx. So m, remember, is negative tan squared theta t. So I'm just going to pop that in there, and times x, and then plus c, which we've just worked out, a sine to the 4t plus sine squared t, and I guess maybe I should just put that a at the front, a sine, that's very messy, let's just fix it up, plus a sine squared t cosine squared t. Okay, now it's starting to look familiar. You know, you can see that I've kind of got where I need to get to. What I'm going to do now is I'm going to multiply everything by cosine squared t to get rid of this denominator here. I want to get rid of that, I think. So if I do that, I will get y cos squared t equals minus sine squared t x plus a sine to the 4t cosine squared t, and then the last one will be plus a sine squared t, and then the cosine will be to the 4t. And I think we are getting close. Yeah, I think we're getting close. So then I'm going to bring the x sine squared t across, and you see on this side, on the right hand side now, I've got this, and I can actually factorize some stuff out here. So let me factorize a sine squared t cosine squared t, and then you'll see in the bracket I'll have sine squared t plus cosine squared t, which is just 1. So then that leaves me with exactly what I want, which is, well, I can just maybe write it in exactly the same order as they've got. That will make it nicer, perhaps. X sine squared t plus y cosine squared t equals to a sine squared t cosine squared t, and that's it. That was a bit of a mission, wasn't it? Okay, the next one's an integration question, and okay, so it is given that integral with limits 0 and a of x cosine x dx is equal to 5, and we know that 0 is less than a is less than 1/2 pi, and we've got to show that it satisfies this equation here. Okay, so first thing that you should notice, you want to be aware of, is that we're actually going to be using the integration by parts rule here. So this here is how we should think of this part here. So we're going to say that that's u, and that's dv dx, which means that du dx is equal to 1, and v is equal to the integral of cosine x, which is sine x. Okay, and now we're ready to apply this part here. So uv is going to be x for u, and then sine x for v, minus the integral of v, which is sine x, times du dx, which is times by 1. Now, let's get the answer to this. We get x sine x minus, and when you integrate that, it should be minus cosine x. So we should get x sine x plus cosine x. Now, we're meant to be integrating between 0 and a, so we want to apply 0 and a to that, and it's meant to equal 0.5. So I probably should have I can put my brackets around here. There we go. I'll do x sine x plus cosine x between limits 0 and a is meant to be equal to 0.5. So let's just do that. So so we should get a sine a plus cosine a minus, now when we apply the 0, the sine 0 is 0, so that's just going to drop out, plus cosine 0, which is 1. So and so next line, a sine a, and then I can say plus cosine a plus 1 equals 0.5. I bring, that's minus 1. And then I can bring stuff across the other side. So I get a sine a equals 1.5 minus cos a. And then I just divide both sides by a to get 1.5 minus cosine a all over a, which is what I needed to get. Well, that was actually relatively easy, wasn't it? Okay, so the next one we're expressing in partial fractions, so we should be experts at this by now. What we're trying to achieve is we want a over 2x minus 1 plus b over x plus 2 plus c over x plus 2 all squared. That's what we're trying to achieve. So the equation we're thinking about here is a multiplied by x plus 2 all squared plus b into 2x minus 1 times x plus 2, and then plus c, which is just into 2x minus 1. Now, my first step here, I would say, let's let x equal negative 2, and this will enable us to find out what c is. So altogether this should give us 11x plus 7. So let's chuck in a 2. You can see that if you chuck in a minus 2, this drops out the a and it drops out the b because you get a 0 there. But the c manages to stick around, so you get negative 4, negative 5. I think you get negative 5c. That's not right with the highlighter, Mr. Kennedy. Negative 5c, and then on the right hand side we get 11 times negative 2, negative 22 plus 7, so negative 15. So this should give us a c is equal to positive 3. And then I would probably let x equal positive 1/2, and you can see there that will drop out the c and the b, right? And so it'll leave us with a. So let's do that. Now I'm getting 25 over 4a equals, and when I put the half on the other side, I'm getting 25 over 2. And so a is equal to 2. And then my last step is to equate the coefficients for x squared. Okay, so if I'm equating the coefficients for x squared, how do we get x squared terms? Well, we can get them from a times, when we get an x squared here, or times b times 2x times x. That's the only way we can get it. And we know that on the other side of the equation here, there are actually no x squared terms, so they've all got to add up to 0. So we know that a is 2, so 2x squared plus 2b x squared equals 0 x squared. So we know that b is equal to -1. Okay, and this gives us our partial fractions. So it would be 2 over 2x minus 1 minus 1 over x plus 2 plus 3 over x plus 2 all squared. And there we go. Now this next one is an integration question, and it's using the information from the previous question. Okay, I should have probably written that for you. This is a past exam, I think all of them are except for the last vectors one, are past exam questions. So this is just relating to what you've just done, so we've got to integrate that. So we're going to integrate with limits of 2 and 1, 2 over 2x minus 1 minus 1 over x plus 2 plus 3 over x plus 2 all squared. Well, when we do that, we're going to get 2 ln 2x minus 1. Oh, actually, sorry, we're not at all. We're just going to get ln because we've already got the 2 there. So yes, that one will become, the first one will become ln 2x minus 1. The second one will be minus ln x plus 2. Now the next one's different because it's a squared at the bottom, so you've got to think of integrating this. So we raise the power, so it's going to become that, and then we times it by the 3, but it's going to be minus 3. You can always think backwards, right? If I'm differentiating this, I multiply this by this, also by that the coefficient of x, and then drop the power. So it should be, I think, this. Maybe I'll even perhaps write it as a fraction still. So I write it as 3 over x plus 2. And then our limits are 1 and 2 here. Okay, and then we can chuck in those limits. So we get ln, now let's chuck in the 2, so 4, so we get ln 3, take away ln 4 minus 3 over 3/4, okay, and then take away, then we put in our lower limit, ln 2 times 1, take away 1, so ln 1, which is just 0, so we'll get rid of that in a second, minus ln 3 minus 1. And then we can say, well, in the first bracket we've got ln 3/4 using our log rules, take away 3/4, minus, ln 1 is 0, so minus ln 3 minus 1, and then we can say, well, that's like ln 3/4 plus ln 3, which is ln, and we multiply, so it'll be 9/4, and then minus 3/4 minus minus 1 is like plus 1, so it's plus 1/4, and that's exactly what we needed to prove. Okay, so the last question is a vectors question. This is the first time we've done one of these. We are given some position points A, B, and C relative to the origin, and we know that vector AB is equal to vector OC, and we've got to find the angle OAB. Now, ultimately, we're going to use this to help us, although we would rearrange it. We would write it cosine theta is equal to A1 B1 times B1 plus A2 times B2 plus A3 times B3 all over the modulus of A times the modulus of B, and then we can use that to find our angle. So pop that to one side for a moment. I want to find out what AB is. AB is equal to AO plus OB, and if we look at our vectors here, AO is just the negative of that one, and we're going to add it to this one here. So what we should get is -2, -3, -7 plus 3m 1, 1, and when we add that together, we get 3m minus 2, minus 6. Okay, and this is apparently equal to OC, which is this one here. And now we can find out what m is. Therefore, m equals 2. Now, vector AB is equal to 4 minus 2 minus 6. Just tidy that up a bit. 4 minus 2 minus 6, okay? We're wanting to find the angle of OAB. Now, just think about that. So, A is the central bit. So, here's A. So, if we can find vector AO and AB, that will be helpful. So, what's AO? We already know what AO is. That's -2, -3, -7. Now that we've got those, we can apply this formula here to find the angle. So theta, the angle between these, will be inverse cosine of, and then let's just chuck this all in. So on the top of our fraction, we have 4 times -2 plus -2 times -3 plus -6 times -7 all over. Now the modulus of each one, so 4 squared plus -2 squared plus -6 squared multiplied by the modulus of the other one, which is -2 squared times -3 squared times -7 squared. Now, when I'm chucking that into my calculator, the other minute, I got 47.2 degrees. Well, there you go, team. Seemed like a long video today. I hope it's been helpful to you. Hope it's making sense. Some of them were a bit tricky. Let me know if you have any issues with my explanations or you need some further help. Happy to help. Alright, team. God bless. See ya.